All right, welcome back. So this is 5.6. Let's talk about analyzing graphs of derivatives. So a couple things to talk about before we get into the analyzation of the graphs. So everything's going to be based on what type of graph are you given. Are you given the graph of the original function, an f of x kind of thing, the derivative function, or the second derivative? So if you are given the original function, here's a couple things you should look out for. And this is obviously not a complete list. These are some of the main things you should look for. If you're given the graph of the original function, identify where in the original function are you increasing and decreasing, because that'll determine where the first derivative is positive and negative. So the location of the graph of the original function where we are increasing, the first derivative is positive there, or decreasing, it's negative. Minimums and maximums in the graph of the original function correspond to critical numbers, and that's where the first derivative is equal to 0. Look for where concavity is changing shape. So where you see it looking concave up, concave down, the positive u, negative u scenario, that's going to be your point of inflection, where again, the positive u shape is a positive second derivative, and the negative u shape is a negative second derivative. Locations where you have vertical asymptotes, corners, cusps, vertical tangents would be where the first derivative does not exist and are important to identify. Now, if you're given the graph of the derivative, same kind of thing is going to happen here. A couple of things allow you to work backwards, though, to go back to the original, in addition to moving forward with more derivatives to look at the concavity. You'll see a lot of times first derivative graphs are very common because they can do both things. They can talk about the original function, they can talk about the second derivative, and they can talk about, obviously, the derivative itself. So where we above and below the x-axis is where the original function is increasing and decreasing. However, where the derivative is increasing and decreasing corresponds to where it would be concave up and concave down. So you got to be very careful. The original function increases when the derivative is above the x-axis, whereas it's concave up where the derivative is increasing. So they're similar but two different ideas. Crossing the x-axis is obviously where you have a point of inflection. An actual min or max, though, is where you have a point of inflection. So critical point for when we cross the x-axis. Min-max talks about points of inflection. And again, same as before, vertical asymptotes, corners, cusps, vertical tangents, all that kind of stuff is where the second derivative would not exist then. Keep in mind, if there is a corner in the graph of the first derivative does exist at the corner. It's just that the second derivative would not exist at that corner, or cusp, or whatever's going on. Okay? Because essentially, the first derivative becomes the function, and the second derivative is now the derivative of that, so then those kind of rules apply to it. Now, you are rarely given the graph of the second derivative, but if you ever are, mainly you're looking for the idea of concavity and how that's changing. Without knowing a lot more information, you can't work backwards 2 steps to get to the original function there. So it's mainly going to be about above the x-axis, concave up, below it's concave down. At the x-axis, it's going to be, second derivative is going to be 0. We really can't answer too much more beyond that. The idea of going backwards is called an antiderivative. We'll talk about that in Unit 6. So technically, you can determine where the derivative is positive or negative based off the area under the curve, but we're not going to get into that all in this unit. That's more, again, Unit 6 and beyond. Now, finally, not very often, but sometimes you're given a table of values, and you can identify things about the first and second derivative based on the table. So you can see that the function is generally increasing or decreasing based on what's happening to the function values. So we have it going from 3 to 5 to 8 to 12, so we can see that this is going to be increasing. So the first row would be positive. Assuming that this table is fully inclusive of everything, because again, you don't know what's happening between 1 and 2, so there could be like increasing but then decreasing, then back to increasing again, so it is kind of tough. But in general, we could say this is relatively increasing. The second derivative would be talking about the rate of increase or decrease, noticing that we're going up by 2, then up by 3, then up by 4. That rate of increase is increasing, therefore the second derivative would be positive if we could assume that there's nothing weird going on in between these different coordinate points, which is why, again, tables are relatively rare to ask questions regarding first and second derivative values. So let's get into some graphs. We've got 8 in total. These are coming from Albert I.O, which is a useful platform for AP students that our school has. So we're going to talk about that. So here we've got this graph that told us the graph of the derivative. Where is the function decreasing? So if we're given the graph of the derivative, the original function is decreasing where we are below the x-axis. So if we take a look at our x-axis, where are we below? Right here. So we are decreasing from 0 to 3 in region A. And it's as simple as that. It's not from 0 to 2. That's where it would be concave down. Or 4 to 7, that's where it would be concave down because that's where the derivative is decreasing. But the original function is decreasing when the derivative is negative, and therefore, since we have the graph of the derivative, where are we below the x-axis? So literally now, we've got the exact same graph, but now we're talking about how many points of inflection we have. So remember, in the graph of the derivative, we're looking for minimums and maximums in the graph for a point of inflection. So we'd have one right here at 2, right here at 4, right here at 7, and then right here again at 9. It doesn't matter that at 7 and 9, those look like sharp turning points. They would still represent points of inflection because they're still showing the changes in concavity. At 7, right at 7, we went from a decreasing to an increasing curve, so we went from concave down to concave up. Even though it would not technically exist at 7, if we did the graph of the second derivative, it would still show a change in concavity shape. Same thing with that 9. All right, so how many points do they have? So it has 4 of them at x equals 2, 4, 7, and 9. All right, let's take a look at a different graph now. So now they're given the graph of the second derivative. Okay, they want to know where is the function concave up and where is the derivative concave down. So essentially what they're talking about here is the original function is concave up when the second derivative is positive. When the derivative is concave down, it's technically the third derivative being negative then. And this is one of the few areas where, again, something like the AP might test you on the concept of a third derivative. So I'm with the concavity of the first. So let's answer the first part of the question to help narrow down some choices. Because these are generally part of multiple choice questions. So I got rid of the multiple choice so we can just kind of answer them. But you'd be able to at least narrow some choices down from this. So concave up is where the second derivative is positive, so we want to be talking about where are we above the x-axis. So from 0 to b, and then d to 8, those are all where we are above. Now, if we want the first derivative to be concave down, we want the third derivative to be negative, we want to show, anytime you're talking about a derivative that's one lower in step, so like second to third, the direction's based off increasing or decreasing. So if I want the third derivative to be negative, I wanted this to be decreasing. So it decreases from a to b, and then from e to 8. So we'd say a to b, and then e to 8, for where this thing would also then be first derivative is concave down. All right, so that's generally how they go through that process. Again, concave up in the second derivative for the original function is where the second derivative is positive. Concave up or down based off the first derivative would then be looking at where in the second derivative we are increasing or decreasing. That's, again, a relatively rare circumstance, but it does show up. All right, we're again given the graph of the derivative, creating this by this triangle and semicircle. Where is the function decreasing? So again, f of x decreases where the derivative is negative. Where are we negative? We're below the x-axis. We are below from -4 to 0. Those are the only locations where this graph is below. It's not based on where is the graph actually decreasing, it's based on where the graph below. So we have to be very careful regarding what type of graph they give you. If they told us this was the original function, that totally changes the answer. Okay, so you have to always go based off what they tell you the type of function is dealing with for that graph. Same graph, so now they're looking for where is it concave up. So this is concave up when the second derivative is positive, so we're looking for where the derivative is increasing. So we can see we are increasing from -2 to 0 all the way up until we get to 4. So -2 to 4, the derivative is increasing, therefore the second derivative is positive, therefore the function is concave up. It's really not that bad once you start getting the hang of what you're looking for. The key is you have to just be able to, like I said, recognize the graph you're given and kind of work with that. So again, we're given the first derivative graph. We want to know when the original function is concave up. That tells us we want the second derivative to be positive. If we have a derivative going to a second derivative, we're talking about increasing versus decreasing. To make it positive, we want it to be increasing. And that's -2 to 4. All right, so we have the derivative here. We want to know where is the function increasing and concave down. So we want to know where is the first derivative positive to make the function increasing, and where is the second derivative going to be negative to make it concave down, where we're looking for where the derivative is decreasing. So Positive first derivative means we are above, so we're only considering all the values above it. Where the derivative is decreasing, that would be from -2 until we get here to 0. So -2 to 0. That's where we are above and decreasing. It's also actually technically the only point where we are decreasing, so they could just simply ask us, where is this concave down? The biggest thing I'd always have to watch out for is when they talk about concavity, it depends on what you're given. If you're given the original function, we're looking for shape. So shape-wise, from -infinity to somewhere around like -1-ish, somewhere around over here, that is the shape of a concave down function, whereas from like -1 on to +infinity, it's now a concave up shape. But if we're given the graph of the derivative, now we're looking at where we're decreasing. And if we're given the graph of the second derivative, we're looking at where are we above or below. All right, so we're given the graph of the derivative. Which ones must be true? Does there have to be a relative min at -7/4, which is right here? So a min occurs when we go from decreasing to increasing, decrease to increase. With the graph of the derivative, since we are below and then above, that is decreasing to increasing, so therefore that is, yes, a relative min. Is it concave down from -2 to +2? Well, that's a concave down shape, but we're given the graph of the derivative, so we are looking for where is the derivative decreasing. And from -2 to 2, it's not decreasing the whole time. In fact, it increases from -2 to 0, so therefore that's a no. And then finally, is it differentiable from -3 to 3? So this is a trap. You can clearly see at -2 and 2, there are those sharp turns. You're like, oh, it's a sharp turn. The derivative does not exist. And that is true. However, this is the graph of the derivative. If you're given the graph of the derivative, everywhere there's an actual physical point and not an open circle hole or vertical asymptote, the derivative exists because it's part of the graph of the derivative. At -2 and 2, the second derivative would not exist because that's the derivative of the first derivative, and that's what happens when you have sharp turns or turning points. But in the original function basis, this is okay. So 1 and 3 would be fine in this particular case. All right, let's do one more. So they want to know, so they're giving this, again, the graph of the derivative. They tell us there's a local max at -5/3. That's just so that we know exactly where that max point is occurring. When it's ambiguous, they'll let us know. Are we increasing from -3 on? So again, we increase when the first derivative is positive. Is the first derivative positive from -3 on to +infinity? Yes, it is. It technically stops increasing briefly, instantaneously at x equals 1, but it starts back up immediately, so that's considered okay. It would only be considered it's not increasing when we go from a positive to a negative value. So if it dropped below, then it would be considered decreasing and therefore no longer increasing. But briefly stopping for a split second and then go back onwards, it's still considered to be an increasing type of function. Are we concave down when x is greater than 1? Well, again, we're looking at, does that mean the second derivative is negative and therefore the first derivative is decreasing? Well, no, exactly. It's the opposite. From 1 on to infinity, the first derivative is increasing, therefore it would be concave up. So that would be a false. And is there a relative minimum at x equals 1? Well, in the graph, that's a minimum, but is that an actual relative minimum? Well, it is a critical point. We're going from plus to plus. We are not changing. We are increasing and increasing afterwards, so it's not a minimum location. All right, so this one would be 1 only. All right, so we've talked about analyzing graphs both in Unit 4 and 5. This is now just a chance to fully get into it a little bit in more detail. Hopefully that helps any lingering concerns you guys had over graphs. We only have one more topic left in Unit 5, the idea of optimization, and that's it for Unit 5. And that's it for derivatives. We're not totally done with derivatives. We'll still use them throughout the calculus curriculum. You'll see them referred to multiple times, but again, is now done with the formal discussion of the derivative after 5.7. All right, so I'll see everyone next time for that video.